Okay. So the screen is getting shared, Gaurav.
Yes.
Okay, cool. So we were discussing now about this complex, right? Hexafluoridocobaltate 3 complex. And
Mm-hmm.
what we just discussed about was its geometry along with its hybridization. Can you just roughly again tell us what we just learned about weak ligands? Are they going to pair up electrons or not? Do
No.
weak ligands
Yes.
have Okay. Do weak ligands have any role in pairing up electrons, or do they leave it as it is in the central metal atom?
They leave it them as it is.
Yes, they leave it as it is, and they do not cause pairing, which is why we end up with outer orbital complex with hybridization sp3d2. This was clear, right?
Yes.
Okay, let's move on to the next complex here. This is called hexaamine cobalt 3 ion. Okay, so we
Okay.
know coordination complexes are written in square brackets, right?
Right.
The first thing that we need to write inside the square bracket is our central metal atom. Here in case we have cobalt. Then we
Mm-hmm.
got to write the ligands that are there around the central metal atom. Now, from the name, what do you think the ligand would be?
Uh, I mean,
Amine,
NH2.
NH3. Amine is ammonia. So we have NH3 as our ligand here in this particular complex. And how many of
Okay.
them would there be? Hexa
Six.
stands for 6. Great. So we have CONH3 whole 6. 6 ammonia ligands coordinated around central metal cobalt, right? And
Yeah.
now we get to decide the charge which would be there outside the complex. Here in the what is that called? Parenthesis, there are some Roman numbers written. Here it is written as 3. That means the oxidation state of cobalt in this particular complex is 3. As a result,
Okay.
what do you think would be the net charge on this complex? What can I write on the right hand side top corner here outside the square bracket?
-3.
Yeah, okay, so here it won't be -3. Why? Let me tell you. Cobalt is in oxidation state of +3. Ammonia's charge
Okay.
is 0. Ammonia is a neutral molecule. It does not have any charge whatsoever. So
Oh,
what
oh.
goes
Okay.
outside? Yes. What goes outside the square
+3.
bracket? Yes, +3. So this complex has a +3 positive charge. This is called as a cationic coordination complex. I hope you got that.
Right. Okay.
Okay, so let's just take these points one after the other, like we did in the previous case. What's the central metal atom for this particular case?
Cobalt
Cobalt, great. What is the oxidation state here?
+3.
+3, nice. What is the central metal ion as a result of the oxidation state?
CO +3.
CO +3, wonderful. One second, let me just, hmm. Can you see the screen?
Yes.
Okay,
Clearly
great.
visible.
So now the next last point, point number 4, what is EAN? Do you recall this?
Effective atomic number.
Yeah, this is effective atomic number. How do we calculate that?
Atomic number
Mm-hmm.
minus oxidation state
Great.
plus the electrons donated by the ligands.
Okay, great. Here, the atomic number of cobalt is 27, minus oxidation
27.
state is 3, plus how
Yeah.
much?
12.
12, because
6.
each ligand donates a pair of electrons, meaning 2 electrons.
Yeah.
So 6 ligands would end up donating 12 electrons, right?
Yes.
And what's the value here? So for EAN,
36.
36. Now 36 corresponds to a noble gas, krypton's atomic number. If we have the effective atomic number matching any of the noble gases atomic number, we say that this particular coordination complex is considered to be a stable coordination complex,
Stable.
and yes, it won't be much prone towards ligand exchange. Ligands won't get exchanged in solution. It stays as it is. It's considered a stable coordination complex. I hope you got that much.
Yes.
Okay. Great. Now we'll actually go into the hybridization of this particular complex. So cobalt in its ground state, what is the electronic configuration? We have already discussed this stuff. Cobalt's ground state electronic configuration is 3d7 4s2 because this is atomic number 27. This has atomic number 27, right? Are you there? Hello?
Yes, yes. Sorry.
What happened?
3D7 4S2.
Is everything fine?
Yeah, everything is fine.
Do you need a minute?
No, you can
Okay,
continue.
cool. So 3d7 4s2. And how do we fill up electrons? Two electrons go into 4s
4S2.
orbital. hmm
Yeah.
And then,
One in each 3D orbital. Then
uh-huh.
pair.
Then pairing. So once we fill each 3d orbital singly, we've done 5 electrons. There are two more. So those two get paired up in two of the 3d orbitals, right?
Right.
Yes. So how does cobalt 3 plus electronic configuration look like? Excuse me.
So first we lose 4S2, two
Mm-hmm.
in the 4S, and one in
Uh-huh.
3D.
Hmm. So
So
4s becomes vacant or it has something.
it becomes vacant.
Great. And how does the 3D look like? 3D becomes, now this becomes 3d6, 4s is 0, right?
Yeah.
So how do you fill up
So
3d6?
so five in Ds,
Mm-hmm. One, two,
and
three, four, five. And
one
then,
is paired.
great, one gets paired up. How many unpaired we have here? Four unpaired electrons. Now,
Yes.
till now, we didn't have a look at strong ligands. We saw weak ligands, which do not alter the configuration of that central metal atom. But in this particular case of hexaamine, the ligand being ammonia, ammonia is a strong ligand, amine is a strong ligand. So NH3 here is a strong ligand, which is why what happens is how many ever unpaired electrons are there in your central metal atom, they get paired up. Strong ligands have the tendency of pairing up unpaired electrons in the central metal atom. This two electrons that are already paired up stays like that, no change. What about the four unpaired electrons? If they pair up, how does the config gonna look like?
So two of the 3D orbitals will be vacant.
Uh-huh. Yes, two of the 3D orbitals are vacant and we get so here, two of the 3D orbitals are vacant. This is going to look a little bit different. How this is different is that now the ligands and the entire coordination complex can use these two 3D orbitals along with one 4s and three of the p orbitals. So what is the hybridization here? D2, because two 3D were used, S because one 4s was used,
sp3.
and P3 because 3p were used, 4p, right? Three
Okay.
of the
Yeah.
4p orbitals were
D2s.
used. So you have D2sp3 hybridization. I hope that's clear.
Correct. Yes, clear.
Yes. Here 4D has no role to play. 4D was for the previous complex. Now, once we have, so here, what is the hybrid orbitals that are getting produced? D2sp3, right?
Right.
Okay. Here also D2sp3. Now, whatever the 3D here, how many 3D orbitals are already paired up? Three.
Three.
So those three orbitals, they're not going to participate in bond formation. They're just going to be there. They'll just chill there on their own. They're not playing an important role in this condition. Got this?
Okay.
And the vacant ones form D2sp3 hybrid orbitals. How many D2sp3 hybrid orbitals are you going to obtain from this particular case?
Six.
Six. So now you have six vacant D2sp3 orbitals. Tell me something, these six D2sp3 orbitals, do they have equal energy or unequal energies?
With equal energy.
They will
Degenerate.
have, yes, great. That is called as degenerate orbitals. Okay. Now, once we've figured that out, just give me 1 second to structure these orbitals. Okay, now it's fine. So you have the three paired up electrons of the central metal atom just as they are. And now in the six vacant D2sp3 orbitals, six of the NH3 ligands are going to donate electron pairs, and they would fill up all six vacant hybrid orbitals, right?
Right.
Okay, so how does this going to look like? This is also an octahedral species because anything with six ligands usually form octahedral complexes. Now, octahedral complex, instead of fluorine, this now becomes all the six ligands are ammonia. So we write
Ammonia.
NH3, NH3, ammonia all the way through. Can you explain how in three dimension an octahedral complex looks like?
So it has a square plane and two pyramids,
Yes, we
upper
have a
pyramid and
square.
lower pyramid.
Great. We have a square planar base with one pyramid going up and one
Mhm.
pyramid going down. Means
Yeah.
one bond above the square plane and one bond below the square planar structure, right?
Okay. Yes.
Okay, great. We have figured out the geometry and shape of this coordination complex. Now we just need to figure out some last bits. What is the magnetic behavior of this complex? Remember, magnetic behavior is spoken in terms of whether this complex is paramagnetic or diamagnetic. How do we decide if something is paramagnetic or diamagnetic?
Paramagnetic has unpaired electrons, and
Great.
magnetic don't have any unpaired
Hmm.
electrons.
So if all the electrons are paired up, like in this particular case, we consider these complexes to be of
Diamagnetic nature.
diamagnetic in nature. Now I'll just take you to the side for a little bit and we'll discuss something. So here, let's say a particular coordination complex has n number of unpaired electrons. So let's assume that we have three unpaired electrons. N is equal to three. That means three unpaired electrons. Now, tell
Yeah.
me something. How are we going to find out the magnetic behavior of this in terms of magnetic moment? What is the formula for that?
Under root n times n plus 2
Yes, n plus 2 over root or under root, n being 3, 3 plus 2, which is equal to 3
and root
into
15
5 or 15 under root. What the unit of magnetic moment mu is in terms of Bohr magneton, Bm, right?
right.
This is how we calculate the magnetic moment of coordination complexes. Now, moving to whether the species, this coordination complex, is it an inner orbital or outer orbital? How do we decide that? Do you have any clue? Can you guess from the previous example whether this is going to be an inner orbital or outer orbital complex?
We took the two of the vacant 3D orbitals, so
Hmm.
I guess it's a three. It's an inner orbital.
Yes, we have taken the inner d orbital of the central metal, the d orbital which already had electrons to begin with, not the outer empty d. We crossed out the outer empty d. This has no role to play in this coordination complex. Now, because we've taken the inner d in the sense n minus 1d, where n is the principal quantum number, which corresponds to 4, because 4s was the outermost electron orbital where outermost electrons were filled. Now, this is also called as the penultimate shell, but other than that, because the inner d is used, this is going to be an inner orbital complex. Okay.
Okay.
Okay, now the last point that we discuss is whether it's going to be a low spin or a high spin complex. How do we calculate spin? What is
Unpaired
exactly spin?
electrons.
Yes, the more the unpaired electrons, the more it is going to be a high spin complex. If there are no unpaired electrons, like in this particular case where we see all of the electrons paired up, this gives rise to a low spin complex because when you have paired up electrons, one of the electrons has plus half spin, the other electron has minus half spin, and when you calculate the total spin value, they cancel each other out and you get spin quantity 0, which is called a low spin complex. Is it clear?
Right. Okay. Yes.
Okay. Is there any other question in this particular example?
Yeah. Like I was asking, inner orbital and low spin. Does it have to be always like this? is there any case where inner orbital and a high spin complex is formed?
Yeah, you would find inner orbital and high spin also in certain cases where even after you have paired up electrons, you cannot pair up all the electrons, and there is some unpaired electron left, and that would cause the complex to be of high spin, although it would be an inner orbital complex. We would see an example like that. So I'll just talk about that particular example right now in short. So this particular complex, chromium NH3 whole 6 with 3 plus. This complex, let's talk about this complex. Okay. Here, what is the central metal atom?
Chromium
Chromium. Great. And what is the oxidation state of the central metal atom? I
plus
think you can
3,
figure it out. Yes, plus 3, because the ligand ammonia, is it neutral or negatively charged?
0, neutral,
Neutral. So that's why the oxidation state of chromium here is plus 3. As a result, the central metal ion that we obtain here is Cr3 plus, right?
3 plus.
Here we are not bothering
Yes.
right now about the effective atomic number. Let's just look at how the electronic config would look like for this particular case. Now, chromium's ground state electronic configuration is how much? What is the atomic number of chromium? Do you remember?
24,
Yes, great, 24. So, what is the ground state electronic configuration? Chromium is one of the exception cases where it, it should have been 3d4 and 4s2, but it's not like this. This is not the case for chromium. It's an exceptional case where you have 3d5, 4s1. Okay, that's because of stability of half-filled d orbitals, right?
okay.
Okay, then how is Cr3 plus going to look like if the configuration is 3d5 4s1 for chromium?
So one electron goes from 4s1 and
Yes.
2 will go from 3d. So
Hmm.
3d3,
3d3
4s0.
config you 4s0 config you get with Cr plus 3. Now let's just do the box representation of the orbitals. 1 second. You can also simultaneously write the configuration on your own and try to figure it out. One, two. How many orbitals are there in D?
5.
3D? 1, 2, 3, 4, 5. Great. And in P, you have 3. So here, this is 3D, this is 4S, and this is 4P. Okay.
Hmm.
How many electrons are there for Cr3 plus?
3.
3 electrons, right? 1, 2, 3. This is how it looks.
Yes.
Okay. Now tell me something. When we have NH3 ligand, is it a strong ligand or is it a weak ligand?
Strong.
This is a strong ligand. It usually causes pairing up of electrons. But in this case, see how many ligands are there? Six. We need six empty vacant orbitals. So
Hmm.
instead of pairing up actually takes energy. Why? Because if you put two electrons together, there would be electrostatic repulsion. Electrons are similar charges. They would cause repulsion, right? So to pair up
Yes.
electrons, the ligands actually spend some energy. But here they do not have to spend energy because already the two of the 3D orbitals are vacant for them, right?
Right.
Do you understand this point?
Okay. Yes.
Have a
So
doubt?
why in the previous case, why was
Hmm.
this point not considered?
In the previous case, that's because strong ligands, they don't want to go to 4D. 4D is way too much work for them. They would like to stay in inner orbital if it is possible. If they can pair things up and take an inner orbital D to sp3 hybridization, they would do that. But in this case, you do not even have to pair up. You already have two of the D orbitals vacant anyway where the ligands can put up, right?
Okay. But in
For
the previous case, we had 4 of the unpaired electrons, which would
yes.
cause two pairings. Here
Uh-huh.
it will cause only one pairing, so the
Yes, here
energy
it
required would be lesser.
okay. Let me tell you in this way. So for example, how do I say? For example, if you have a train seat or a train bench where there are positions for three people, and a
Mhm.
person is there, a mom is there with her child, the mom can take the child with itself, and that would make two places vacant where you and your friend can sit, right? That's
Right.
one case. That's the first scenario. But in the second
Mhm.
scenario, if already there are two vacant places and only one person is seated here, that may be a male or a female, that does not matter. If only one person is seated here, you would not want to move or maybe let's talk about it like this. If there are already two people seated there, but you're just one person, you're not traveling with any company, you're just a solo traveler. Would you want to pair them up and take two vacant seats? So
No.
asking people to pair up would actually make you request them, and they would maybe accept your request or may not accept your request. Why would you even go to all those lengths when you have a place where you can, put up and sit comfortably? That's why
Okay.
here the ligands, they don't have to do that much work because they are already finding two vacant spaces, right?
Okay. Okay. Yeah.
So they take D2 sp3, this 4s, this 3d, and this 4p. 3 of the 4p, 1 of 4s, 2 of 3d forms D2 sp3
Quickly.
hybridization. Okay,
Okay.
this
Yes.
is clear.
Yeah. Now it's clear. Thank you.
Any doubt in this particular case?
No. Okay. Now.
Okay, okay, great. So this is done. Now, when we have a D2 sp3 hybridization, what does hybridization mean? Is that they would all have equal energies. The hybrid orbitals would have equal energies. And how many orbitals will be produced as a result of this particular
6.
hybridization? Six. One, two, three, four, five, six, right? And then
Yes.
these three, which are there, which are undisturbed, which are there, the 3D electrons of the central metal, they just lie unaffected. Now, once you have D2sp3 vacant orbitals, the ligands, 6 NH3 ligands can place 6 electrons into those hybrid orbitals. That's clear?
Okay.
Okay. Now tell me something. What's the magnetic behavior going to be? Is it paramagnetic or diamagnetic?
Paramagnetic.
This is paramagnetic because of three unpaired electrons. Yes.
Yes.
And is it a high spin complex or low spin complex? This
It
is
will
a high
be
spin complex because there
okay.
are three unpaired electrons and the
Uh-huh.
spin value would be half into
Half.
3, 3 by 2, 1.5. 1.5 is considered as a high spin complex. But here, the question
Okay.
that you asked earlier, this is a case of inner orbital complex, right?
Right. Right. Inner
Why is it
orbital and high.
inner orbital with D2sp3 hybridization? Why inner orbital? Because it's using the inner 3D orbitals of your central metal atom, chromium here in this case. Yes, and not
Yes.
the outer 4D orbital. That's why in cases like this, where you do not have to do pairing, where the ligands do not have to do pairing, you would find its spin to be high, but the complex to be of inner orbital nature. I hope this is clear.
Yes.
But as a thumb rule, as a general thumb rule, we like to say that strong ligands usually form inner orbital complexes with low spin because mostly they pair up electrons and you would rarely find any unpaired electrons. But certain cases, so elements with less atomic numbers, titanium, vanadium, chromium, they usually form higher spin complexes, high spin complexes because of unpaired electrons, but inner orbital in case of strong field ligands. Got this?
Okay. Yes.
Any doubt?
Thank you. No. Okay. Now.
Okay, thank you.